You know, I'll start by saying I was at one of the IPCC meeting in Germany, and the other people were talking about wind and various other things, and geothermal was always sort of a set on a back burner, and so I wondered why is that geothermal has such a poor recognition. So I did my own sort of market survey, asked various people, what do you understand by geothermal? And she said, the lady or man said, oh yes, Iceland, New Zealand, all the other places they've thought about, but they never think the geothermal associated with your own country. So it really surprised me how unknowledgeable or lack of knowledge we have on geothermal. So mine is slightly extended presentation. Well, I looked in there that maybe not everybody is familiar with it. So I'm going to try and guide you through like a PhD thesis from beginning to the end, and I hope I'm able to convince you it's worth pursuing. As David said, I've been at it for 30 years. I started my career with BGS, looking for a site for nuclear disposal. This was 1970s. We're still looking for it. Now, the talk is generally in sort of a four. Why do we were looking for? The demand and supply of energy, definition of concept deep geothermal, what experience we're going, and how do we go to commercial. So now I'll have to come over to this one. This is a Shell study a while back, and this is a demand curve. This is about 10, 12 years ago when Shell were involved in the European project. That's the demand there at that time, and that's the supply. And you can see, although the curve may not be exactly the same, but the general trend is going to be very similar. This is all sort of, this is coal, oil, gas, hydro, nuclear, all. And they started to get worried that really we need to bridge the gap. When anywhere in a commercial system, when the demand outstrips the supply, the price goes up. And you can see here, already we're talking about £1.50 a litre for diesel. And you are talking about here, 15.50. Can you see the problem if we don't? If we don't bridge that, I think it'll be more than just prices going up. I suspect there will be conflict, international conflict, because nobody wants to be lack of energy. So unless we move forward and come with a solution to bridge this gap, there is a potential problem. And just to explain, this is taken from, I'm also advisor to US DOE on energy and other things. And this is a cartoon which I thought was fantastic. We think about Earth as a non-resource. But actually, once you take the crust, the amount of heat stored in Earth is just phenomenal, far beyond your imagination. You can see the Earth is obviously the crust, mantle, core, and inner core. And if you take here, like I think it's about 4 kilometers, you can 2,000 kilometers. But what I'm trying to say, look at the 4,000, 5,000 centigrade. Even if you play around here right at the top, you can get very high temperature. And the amount of heat stored is phenomenal, and you get a conduction. So all this heat that we have, and we haven't tried to do anything about it. So what we're trying to do is to change that. Geothermal, I don't know when I get it, sorry. Geothermal can be broken down roughly into three. I think the one that's the most commonly used, aquifer, like in Paris Basin and other places, for space heating, or ground heat pump that we talked earlier on. Then there is the one that's used all over the world, which is called hydrothermal, and I will explain. And the last one is an engineered system. It started originally in Los Alamos, rocket scientists sitting, cups of tea, and they said, look, hold on a second. If we go deep, as we go deep, it gets hotter. Everybody said, yes. Why can't we get the heat out to generate power? So this is how it started. So Los Alamos started in about 72, 73. Similar program in UK started in 76 as a research project at the School of Mines. And then Los Alamos defined the term hot, dry rock because there wasn't any water. Japanese didn't like it. The Japanese rephrased it to hot, wet rock. And when Shell started working with us, they decided hot fractured rock. And then Later on, the US redefined this to engineer enhanced geothermal. But one of the key things in this is geology is such a complex thing. You can't have the same solution everywhere. There has to be slightly tinkered. So I coined the phrase engineered geothermal system. So when you go there, you engineer a solution to whatever you see. That covers a large range of different conditions. This is a hydrothermal system, which is normally the crust is fairly thin. Like in New Zealand, they're on the tectonic boundaries. So you have a rainwater going down, accumulating here, yeah? And because the crust is thin, you can get anything between 200 to 300 degrees centigrade. And if you discuss with the Icelandic, they want to do supercritical, which is over 500 degrees centigrade. So you can get a large amount of hot water. And in a hydrothermal system, you have to locate, like in oil sort of hydrocarbon industry. This industry is very, very similar to hydrocarbon industry. You find the resource, and you drill a borehole, and out comes the water, hot water, and then you have a turbine on the surface to convert it into electricity. But as you can see from this diagram here, this is California, that's New Zealand, that's Iceland, that's Italy, so Greece, to some here, some in Kenya, Rift Valley. But these are all specific zones. Now, industrialized nations like Germany, Europe, Britain, all this area here and here haven't got that specific topic. So although we have a heat, but we haven't got ideal condition to get the heat out, but the heat is there. So we need somehow to mimic what happens underground by engineering this process, to develop a process underground to be able to get the heat out. It's IEA is International Energy Agency, the geothermal side of it. They recognize that the hydrothermal is an important, is a low-hanging fruit. If you have it, you can do it. There's no problem. But you really need to get the discussion and evaluation suggest that engineer EGS has got a tremendous potential and a significantly huge resource. And this is sort of some figures initial. Global estimates of geothermal potential. Hydrothermal is 1 terawatt electric. Non-electric heating, ground heat pump is 4.2 terawatt thermal. EGS, this is under discussion. It's 4.5 times that one. If not, I should think it's double that one if you go deeper enough. And this is their supercritical like the one. And to give some comparison, 2006 worldwide electrical generation was 2.1 terawatt. So you can see it's a huge resource. And it's applicable in a large parts of the world. Well, what does it consist of? Principally, you drill a well to the temperature you want to go. Particularly, there are areas in Cornwall where you go to 5 kilometers near Land's End granite. You can get 220 degrees for 5 kilometers. If you go other places, it depends. So you decide how deep you want to go. You drill a borehole, and then you inject fluid to enhance permeability. Because normally here, if you fill the well up, it will not move. A lot of times it's called closed system. The water will stay in the well, it will not permeate. But when you inject it, it will start opening up these features. We are opening up existing features. It's almost like having your two knuckles together. And because of differential stresses in the ground, when you inject water, it slides slightly. And as you can see, that gives you permeability. And that permeability can be up to 30% more than what it was. So you drill a well, do the stimulation, enhancement, and monitor this with acoustic emission using seismic sensors. And then you track where it's going, and you put your second well and a third well. So basic principle, you go, water goes down, cold water, goes over these fissures, gets heated up, comes back to the surface, goes to the turbine, and goes back. So it's a closed loop system. So it's a very, very simple, very effective. So that's the idea. To get some idea how much heat is in a rock. So if you take a granite, for instance, if you take a 1 kilometer cube and you drop kilometer cube rock from 200 degrees to 180. The reason for that is because your binary plants that you put on the surface has a range from each efficient. If you go below 180, it becomes inefficient. So that 20 degree is based on the binary plant. So if you drop that, that is equivalent to, you can see here, either you want 1.3 million tons of oil or barrel. So you're talking about a huge resource. It's not a puny resource. And I was involved in a study, similar study done for MIT. And they wanted to look at the resource in the US. And they did, I think you can download this report from MIT. And somebody, one of the guy in the US DOE did this diagram. It's very difficult. If you put figures, it doesn't mean anything. So the idea is that if you put all the resource available in the US as a barrel, you find something like 98% of it is geothermal. And they go up to 10 kilometers. Let's assume, okay, that's too ambitious. Let's cut 60% off. It's still bigger than anything you can imagine. So there is a drive in the US to get more handle on geothermal. Now, this figure is not peculiar to US. You will find this is similar in lots of countries. We did some evaluation, Korea, Japan, and other, they come to the same figure. There's a massive resource not used. For Europe, this was funded by European Commission. This is only up to 5 kilometers, not deeper than. UK is here. That bit here, that bit here, that bit here. These are the temperature. The red, the darker colors are about 160 degrees at 5 kilometers. The Sulz that I worked on, the Sulz project, is here. So I worked from 1980 to 1990 here, funded by DTI at the time. And then John Garnish moved to Brussels, and he really recognized a project like this needs lots of funds. It can't be done on a shoestring budget. So he was able to bring all the nations, German, French, Britain, and others, together to work on that one, and that changed the equation completely. But even at just general topic, the high resources obviously in Turkey and Greece and Hungary, these are the primary, huge. But even as you moderate figures, you're still talking about 130 gigawatts. Just a moderate term, this is 130 nuclear power station equivalent in Western Europe. Only 5 kilometers, we're talking about super deep or anything. And an economy of worth, I think, a figure of 45 billion per year. So you're not talking about a small amount. Now let's talk about the definitions. How did it start? We started Los Alamos in our state. We adopted the idea from oil industry, which is let's have a borehole, yeah, 2 borehole, and inject fluid in here. The idea is like in oil industry, you create a penny-shaped crack connecting one borehole to the other. Yeah. So it started like that, a penny-shaped crack. Where then the project in UK worked with Los Alamos together because they went too hot, too deep, problem with technology. We in UK wanted to understand physics associated with it. So when we injected fluid in here, we found it doesn't work like that. The shearing takes place. The rocks, existing joints slide and create the permeability. And we were able to define, we understood a lot about it, how the stress and others also control it. So we were able to find out what was the physics associated with it. So from that one, we used this know-how because in 1992, the project in the UK was terminated, so it moved to Sulz, which was a European project. So we decided if you have a borehole, if you inject, the fluid migrates both ways. So we can double the output by putting 3 wells.
Can I, I'm awfully sorry, I'm enjoying the lecture enormously.
But you want to...
we will, if we're going to have any discussion, do you think you
I can accelerate,
to
yeah.
a conclusion in the next 3 or 4 minutes or so?
Well, I thought it was a 40 minutes talk, or at least half an hour presentation. No?
It is supposed to be a 20-minute session.
All right, okay, I'll move fairly quickly.
Yeah.
Well, like as you can see, Prince Philip visited the project in 1986. Well, I will just go quickly. We were successfully able to demonstrate in 1997 that you can circulate a system. We were producing electricity, heat. Industry came and said, no, they didn't want that one. They wanted deeper. So we extended the borehole deeper to 5 kilometers, and we were able to create 600 meters deep, another system. And I'll see if I can show you a little bit. Never mind. What it shows is that this, we've gone, I'll forget that one as well. So we created this system in the salts, showed that it can do at 5 kilometers and so forth. So my German colleague moved 20 kilometers further north, and this is the first commercial system where he's got a borehole going down, water comes up there, goes to first heat exchanger, produces power, and then goes through second heat exchangers, does the space heating, and down there. It's taken 3.5 years to do it. He was fairly modest in his temperature, 145. He went 3.8, 20 million pot, and he produces between 3 and 4 megawatt, and it's continuous ever since then. And that spurred off a lot of other commercial projects all over the world. For UK, the study shows that something like 10% of the UK's electricity can be produced for 200 years from geothermal. This is the team. So this is to do with the Eden project. We got 2 boreholes, and that's exactly as in Landau we planned. And the idea is to supply, I'll go through. This is the Eden project, and the idea is to supply electricity and heat to the Eden project. We could have selected other places to go to improve the economics, but we wanted to demonstrate in the UK that this is environmental friendly, it's a very small footprint, and mostly economically viable. That's what David said. That's the car park that you can see. There's the rig layout and all the rest of it, the mud pools for drilling. And we changed. Normally in the past, people usually always wanted heat, geothermal to produce electricity, but we've combined heat, recreation, crop, and eco-town. So we're trying to disperse it much wider. And also in the past, each project has been built like a handcrafted item. We want to change that completely to more like a production engineering. We have 3 different sites, drilling rooms moved from one to the other to bring the cost down.
Boy, I can feel the tension from the chairman on my right.
I'm nearly finished.
It's terribly relaxed, but how can we put it that way?
Okay, nearly finished. It's quite clear that this sort of what I'm just trying to say, this is not 4 to 8 megapound. We're discussing in the oil industry that it needs to be scaled up. Those, like the salts, if you have 1 plant, 2 plant, 3 plant next to each other, you could produce 15 megawatt. And if you can stack them up next to each other, 45, and you can have even bigger. So it's a scaling exercise. It can only be done with a big industry. And this is perhaps the last one, is we did this, created a reservoir here, system here, we created a system here. This is a new idea. If you have 3 systems, one below the other, you can run this for 25 years, then you use this 25 years, then the third one. By the time you finish, in 75 years, this will be charged again. So you can go that forever, as long as you like. And this is CO2. This is from IEA again. This is coal, oil, gas, today geothermal, and this is our new technology here. That's what you're trying to see. Virtually no, because a closed loop system. Well, I forget, the CO2, you don't. Because the same technology can be used for CO2 storage as well.